In this video, I'll be trying to solve a bearing problem. So first, we need to know. I have a little bit of background of bearings. So bearings, if I'm talking about specifically for this scenario, they will be installed just here to avoid these two materials, whatever this material is, and the shaft from grinding. So we put it either they could be cylindrical, or they could be just balls, or they could be two rows of balls, okay, or they could be just cylindrical. So they're installed here. So it's part of mechanical engineering responsibilities to select suitable bearings that will last and that will suit whatever application that you are trying to achieve. So there are a lot of standardization that comes with the whole science done by SKF, which is the company that design and manufacture, also distributes the bearings and all other appliances. So okay, it's not an advert, so let's just remove it. So let's try to read the question first. Below is shown a gear driven squeeze roller that's made with an idler roll. The roll is designed to exert a normal force of this much. So if there's, it's like a roller, so I'm like, say we are putting something here, this thing will kind of squeeze it. So there's a normal force of 5.2 5 n per millimeter, okay, and then with the pull of, okay, so there's another one that is pulling, like that's pulling in whatever that you are trying to squeeze in there. It is 4.2 n per millimeter. Okay, cool. And then we are given omega, which is 300 rev per minute, and then we are given life of the of this or it should run this much, just at lifespan. Okay, so it's going to be 30 kilo hours. Let me just put three zeros. Use then application factor of 1.2, and then select a pair of angular contact series. They're giving us the type of bearings that we're getting, so we're trying to get ball bearings, and the table that will be mounted at A and O. So I told you how they're mounted there. So literally, let me say there is a shaft here. I'm very not an artist. Okay, so your bearings will be something going, maybe there will be a ball here, and there will be another ball here, and then this thing will be holding these balls like that. So this literally a cut out view. I'm literally cutting it like a pie, like this. I'm cutting it here. So there will be balls all around the shaft. So it's either there are two rows or just one row, depending on the application and what you're literally trying to do. I don't know what you'll be trying to do. So they gave us reliabilityness of 0.92. So let's start working. So what else we know that is useful that we're going to need? We know that xd is going to be omega L 60 all over 10 power 6. Okay, so we know our omega is like 300. Okay, I think my omega needs to be in, okay, I think 300 is fine. 300. And then here it's life, of which is going to be 3000, 30,000. Then I'll have 60 all over 10 power 6. then you punch this in your calculator. Hopefully I didn't make any mistake on my calculator. So, okay, and then I got an answer of 540. So these are all the parameters that we actually going to use on finding the right bearing that we need for our application. Okay, let's just put that aside. So our next step will be trying to find all the forces that are here, of which will be reaction A, Y, and reaction A, Z, because I think this is Z, this is Y. So I'm assuming that this thing is not trying to move axially, so we're only focused on the radial load, not axial. It's not trying to push in like this, but it's only moving their forces on the X and Y, so I mean the Z and Y. So it is worth noting that these forces that they give is they're not really forces, but they are forces per some unit. So that means we are going to have some, let me call it PY. It's going to be, is it PY? Oh yes, PY. Y is this one, right? Y is up and down for the scenario. So it's going to be, I said that normal was 5 to 5 multiplied by the length that this force is acting upon. So it's that force that is needed for, or that force is used for rolling. So obviously it's the size of the roller. So the roller they gave us here, if you look into the dimensions, we are seeing something like 200. So let me just plug in my pen. 200. Cool. Then if you calculate, you can turn 50. Now it is the right thing. So PZ, also Z is this one, right? PZ is going to be, it's the force that this thing is using to draw in whatever that is trying to, I don't know, slash in, I don't know the good word for it. Then it's going to be 4.2 multiplied by still the same length of the roller. 200 is equals to, then after computing I get 840 and cool. So now we have the forces. So what else we are given? Also we can get the torque since this thing is drawing in. Let me look at it from the side view. I just don't have space. This is the shaft, and this is a roller, and this thing is literally pushing in everything inward, whatever that you are putting in here. So there should be a force, right, of this nature, and it should have some sort of arm. An arm should be the same as the radius of the roller, and they gave us the roller's diameter. I'm not too sure if, I think I did see it. Oh, here it was 100. So this force, we're going to use the force Z, and the arm which will be radius of the roller. So we'll get the torque along the axis, which is going to be, that's 840 multiplied by the arm or the lever, of which is 50 mm's. So I'm using everything in mm's. Then if I compute here, I'm getting 42,000 m. Let me get another page. So now because along these axes there was this force here, and there's also a force that is applied on the gear here. See, it's more like the force that is driving the whole system. So that force is applied at some angle, so we can say the torque caused by this should be the same as torque here. So whatever the power the thing has to throw things in it, it should be supplied by pushing in by that force F. So I think it is a good thing to say that 42,000 should equals to these are moments, right? Moment caused by this one. So this one, the moment caused is only looking at the adjacent component, of which is going to be F cos 20, but we want to have an arm should be 50, right, if I'm not mistaken. No, but now this one, it's on this thing, it's not on the big roller, it's on the small gear, and the gear has its own diameter, of which is 76. Then we can half it, and then if we half it, we're getting 38. That's 38. Then from here you can solve for F, dividing both sides with whatever, and then we can now get the value of F to be 1176.2 newtons. Remember, the force that we are getting here is this force that is applied to energize the whole system. So we still remember our goal is getting the force reaction on the where our bearings are going to be applied, because literally that's what we want. We want to know how much force this bearing should be able to withstand. If and then and selection choices will rely on that. So let's try to get reactions. So let's try to take sum of moment about point naught. Let's take it along z axis. Okay, so because this thing is not moving, like not pivoting around 0, so all that moment should be 0. So let's try to do it. Let's come back here. We are taking moments about this point, looking at which axis? I said z axis. We're looking at only this plane. Okay, so that's clean. We're looking only in that plane, forces in that plane. So the component here, the F cos has some impact, so let me call it F cos 20. But now for moments we need a force and the arm. The arm here, it's going to be this 45 plus this 200 plus this 45 plus that 70, and if you add them, all of them up, you're going to get what's the number? You're going to get 360, right? And that's negative because of my choice of direction. Nothing much, means the other ones will be positive. And then plus, let's look at the other force. This is the other force that is there. We could look at there is a reaction by a, let me call it AZ. Okay, AZ will be there. Let me call it AZ. Also we need a lever for it. What is a lever? It's going to be that 45, 200, 45. I think that 290. So it's going to be 290. Okay, cool. Also, am I missing any other forces in that plane? Let me think. Also, because I'm in this plane, that force that is literally pulling everything in is also in that plane, so we need to take into account for it. So it's going to be in the somewhere here. It's going to be in the middle. So that will be a force PZ. It's PZ, right? Yes, this one. It's going to be this one, PZ plus PZ, but PZ should have some sort of an arm. It's going to be this half of this 200, and that 45. I think that's 145. 145. Okay, I think I made a mistake on my signs. This force is like this, that is like that, and that is like that, meaning all my forces should actually be negative. Yes, yeah, I'm good now. So how many forces? I think I've covered all the forces that I have. PZ, I have the force that is applied on the gear, then this is all equals to 0, and then you can solve here and you get your RA, reaction at A along Z, to be negative 790 newtons. So now it's a force in the 3D space. You should have more components. You can't just have a Z1, so we need another one, a Y1. So for a Y1, we're going to take moments again on point O, but along Y, on the Y plane. So now we are actually focused on, I don't know if I can draw it so good. We are focused on that plane. So looking at the forces that exist in that small span of space. Okay, so obviously now this force here will be involved. The opposite which we'll be using sign now. Also the normal force here will be involved, that we talked about, the one that is pressing. The reaction will be involved. So we have literally have 3 forces. I'm hoping that I'm cool. Then should equal to 0. So what we want to have first is the normal force. The normal force that this thing is exerting here, of which is this one that we computed first, of which is 1050, and it is an arm of 145. Remember how I made the 105 from the past part. Then we have the reaction is A along Y. It's going to be that reaction, and the arm I think it will be 45, 245, making it 290. Then subtracting this moment by this one, so it's the only one going up. We're expecting only one to be negative 360 F cos 20. Oh, it's now opposite, so it's sine. Okay, we know everything here. We know this one except this one, so we'll have R L Y to be equals to, and then if you compute, or funny, to negative 25.6 n newtons. So we now have all the forces. You could continue and do the sum of all the forces along Y, sum of forces along Z. You could now try to find what are the reactions on the other side, O, because we're focused on A, but A is sufficient enough for teaching purposes. Okay, so after that we can now substitute into our formulas, and then try to decide on which bearing are we going to use exactly. So we are literally going to do a lot of substitution. Okay, and until now it's just you with your data sheets and the tables, and then you substitute everything, and then I think the hard part of the problem is already conquered. You could just finish up from here. So it's just data now. That is 1/3. You know that if it was a roller, you have used you'd have used 3 all over 10 here on the exponent. So that's literally your data sheet for formulas, nothing much. And then here we'll get 21.59. So maybe you like obviously here after getting the RY and the ry, we're supposed to get the actual r, of which is going to be ry plus rz squared. That's just Pythagoras, so I just skipped that because I felt like you just know after having components you could do everything. Then you can get our force in the bearing, of which is going to be 1.2 multiplied by the answer that you get out of the actual magnitude of the force there, of which is going to be 17.92. Then if you multiply, you get this number here, of which is FD 540, the very same that you plug in here. So if you go to your tables, of which I don't have with me here prepared, so you'll choose the bearing 3-0235. okay, remember we're looking for good lifespan and whatnot. Also take note that these bearings perform like this if they are in a good condition, where maybe they are properly lubricated and well taken off, they were installed properly. So you can just go through the SKF websites for all these parameters in the table and how to select if you want properties for each bearing that you are looking at their lifespan and whatnot. Yeah, so other than that, thank you for watching.